Welcome to part 2 of my talk, Drilling Dynamics Matters for Drilling Performance. In part 1, I had 2 examples involving hydraulics. Part 2 is on drill string dynamics, axial and rotational. First, axial motion, and the difference between surface and downhole axial motion, and what happens when it is important to know how the bit is moving, for instance, during logging while drilling. The drill bit, and hence the logging measurement, can move faster or slower than the top of the drill string. If the block is moved down fast, for instance to deliberately increase weight on bit, the block can move a decent distance, but during this time the bottom hole assembly has barely moved, so the position of the logging while drilling measurement, shown in red, has changed much less. On the other hand, if the block movement is stopped, the BHA will continue to drill ahead as there is still weight on bit and the drill bit is rotating. So while the block position is unchanged, the position of the LWD measurement is moving. If we want good logs, this needs to be corrected for. When the block is stationary, it is something that people in the drilling world will be familiar with, a drill-off test. The block is stopped and the weight on bit then declines exponentially as the bit continues to drill ahead. The inverse of the exponential decay constant we shall call the drill-off time. But what happens when the block is moving but its speed is changing? Here's a synthetic log of block height with some varying speed and including a period when the block height doesn't move. Differentiating, we get the block velocity, also known as the surface rate of penetration. To get the bit rate of penetration, we must convolve the surface ROP with the drill-off exponential, which is the same as applying a one-pole low-pass filter at a frequency of 1 over the drill-off time, which you see here in red. For constant or slowly varying rock properties, the bit ROP will be much smoother than the surface ROP. To get the change in bit depth, integrate the bit ROP. Now let's see what happens to a synthetic LWD log during that drilling interval. Here's the log versus uncorrected depth from the surface ROP. And here's the corrected version. And here they are on the same scale. You can see that the feature at near depth 9 was virtually removed before correction, as it was being logged when the block was stationary. Other features have moved significantly, or their width has changed. Important if this is the pay zone. This is a very simplistic example, and of course rock properties do vary. This simple method can be extended to varying rock properties and varying surface rotation speeds. The relative depth differences can be very significant. If the weight on bit changes by 20,000 pounds for a 10,000 foot 4-inch drill string, the change in pipe length will be about 3 feet. If multiple LWD tools are present, they log different depths at the same time. So the effects of correction will be seen at different depths on different logs, which can be checked for lithological compatibility. But there is a simple solution when drilling with an auto driller. If weight on bit is constant, then surface ROP is the same as bit ROP. So if you want good LWD depth logs, set the auto driller to constant weight and check that the weight is staying constant. Okay, changing drill string length matters for logging, but does it matter for drilling performance? This is what happens every stand. When the block reaches the bottom of its travel, more pipe must be added. Here's where the block is. What very frequently happens is that the block is immediately raised, so just before it moves up, there is full drilling weight on bit. Up comes the block, and the bit comes off bottom, but now with 0 weight on bit, so the drill string is longer. The bit doesn't come off bottom until weight hits 0. Back on bottom, and the block doesn't have to go down as far as it went up to touch bottom. Like with objects in your rearview mirror, the whole bottom may be closer than it appears. Which brings us to the final topic, related to rotational motion and the initiation of bit rotation. Starting with what happens in a vertical well. the top drive starts rotating, and the rotational wave moves down the pipe at about 3,000 meters per second, slightly less than the speed of shear waves in steel. And once the bit is brought up to speed, only a small amount of torque is needed to maintain motion. It's different in a deviated well, especially so in a long horizontal. The drill string is lying on the bottom of the hole, and the weight, combined with friction, means a large torque is needed to maintain motion. But how long does it take between the top drive starting up and bit rotation commencing? The pipe is compliant rotationally. It twists when torque is applied. To get torque into the pipe, the top of the pipe must turn through an angle proportional to the applied torque. The torque required is going to increase roughly linearly with the length of the horizontal. The pipe compliance is also increasing linearly with total depth. Here's a toy case, just looking at the pipe side force, including some buoyancy correction, for 4.5 and 5-inch pipe, ignoring tension side force and the extra contribution of the BHA, which will increase the angle needed. There is a 2,500 meter vertical section and a friction coefficient of 1/4. The angle is going to be linear in friction coefficient. On the x-axis is the length of the horizontal. On the y-axis, the total angle the top of the drill string must turn through to initiate rotation, measured in total rotations. As you can see, for long horizontal wells, this is going to be a significant number of rotations. If you are not turning fast, for instance with motor drilling or just running into hole, this is a long time. At 60 RPM, the y-axis is the time in seconds. One thing I should add is that this assumes that every time rotation starts, all the torque needs to get into the pipe again, and none is trapped by friction when the pipe stops. I have done 4 simulations including this effect, and it is relatively small. We could convert this time into an effective speed, i.e. the rate at which the point where the pipe starts moving proceeds down the drill string. These speeds are much slower than wave propagation speed for both axial and rotational waves in steel, and get very slow indeed for very long wells. Let's see how this can be a problem. Consider the sequence of events when restarting drilling after a connection, or when rotating into hole. First, the case of a short horizontal section. Rotation starts, so the top of the pipe starts rotating, and a rotational wave starts down the vertical section of the well at about 3,000 meters per second. Then, the driller starts moving the block down, and the top of the pipe starts moving down. Now that the rotational wave is in the horizontal section, the point of first motion is now moving at about 1,000 meters per second in the horizontal. It doesn't matter if the bit hasn't started rotating yet. So long as before the axial wave arrives at the bit, it is rotating. And it's all good. The bit is rotating and moving forward, smoothly going on bottom, or along the wellbore if running into hole. But what about in a long horizontal, especially when everyone is in a hurry? Like you might well be if you have thousands of meters of pipe to rotate into hole. Just as before, rotation on, and the pipe starts rotating. The rotational wave is moving down at 3,000 meters per second. Then the block starts going down, and the rotational wave has reached the horizontal section, but it's still got a long way to go, and the point of first motion is moving slowly. This time, the axial wave gets there first, and instead of the bit moving, it's like being on bottom. Compression builds up behind the stationary pipe. Finally, the bit starts rotating, and when it does, the compression in the pipe above the BHA is released, and the bit and BHA jump forward. If you are going on bottom, this can mean the bit smashing into the hole bottom. And of course, if the driller came straight off bottom without drilling off any weight, the hole bottom may be very close indeed in a long well. Running into hole, there isn't a hole bottom to hit, but as the block will normally be going down a lot faster, it's a lot more motion, and you can have a great deal of compression in the pipe above the BHA. Which brings us to the conclusions. Maximising drilling performance is not just about optimising set points. During changes, whether in drilling parameters or at the bit, surface and downhole measurements behave differently. Optimizing performance during these changes comes from physical understanding of the elastic behavior of the system. If you want more like this, please watch my series of 10 lectures on drilling dynamics.